Hello everybody, welcome into another lesson. So today we are going to talk about some very important trig limits and some very classic trig limit problems that you may encounter in Calculus 1. Up first, we have a classic here, the limit as x approaches 0 of the sine of x divided by x equals 1. This is a fundamental limit identity to use, and if we look here on the screen, I'll zoom in even more. As x approaches 0 of the sine of x divided by x, that's the function on the screen, you see the y value goes to 1. So graphically, this proves that the limit as x approaches 0 of the sine of x divided by x equals 1. And then we have the limit as x approaches 0 of the reciprocal function would equal 1, and that makes sense because x divided by sine of x is simply the reciprocal. But nonetheless, I am going to graphically prove what I'm saying. I don't expect you to just take my word for it. So let's put that in here. Let's graph that. Let me zoom in some more so you can see it. So yes, as x approaches 0 of x divided by the sine of x, you end up getting a limit of 1. So this graphically proves that that function also has a limit of 1 as x approaches 0. Those are both very fundamental identities. Now let's talk about the cosine of x divided by x. There's a reason you're not going to deal with it very much. So let's graphically prove why this limit doesn't exist. Alright, so this is the graph of the cosine of x divided by x. As you see, as you approach 0 from the left, you're going towards negative infinity. If you approach 0 from the right, you're going towards positive infinity. Well, in order for the general limit to exist, the left-handed limit has to match the right-handed limit, and it clearly doesn't. And we see that graphically, so the limit as x approaches 0 of the cosine of x divided by x does not exist. Now there are two more fundamental limit identities we're going to talk about. The limit as x approaches 0 of the tangent of x divided by x, and the limit as x approaches 0 of x divided by the tangent of x. So let's do that tangent of x divided by x first. I know in yesterday's lesson when we tried to do it to infinity, that was just a hot mess, but it's a little bit nicer at 0. Now, maybe I should zoom out for this one. As you see, as you approach x equals 0, from the left and the right, you get a y value of 1 for the tangent of x divided by x. So graphically, we've proven that the limit as x approaches 0 of the tangent of x divided by x equals 1. And it would make sense you would get the same limit for x approaches 0 of x divided by tangent of x because it's the reciprocal function. But again, I don't expect you to just take my word for it. Let's do it graphically. And it's just as hideous as I thought it was going to be. If you approach from the left and the right both towards x equals 0, y goes to 1. So those graphically prove that the limit goes to 1. Now, I'm going to transition over. We're going to do some problems with these fundamental identities. Yes, these are very important fundamental identities indeed, but why are we studying them? Well, you're about to see. Let me set up the screen here, so bear with me a minute. Alright, yikes. Whoops, I did not mean to do that. What I meant to do was move this over and expand the screen so I could see what I'm doing better here. There we go. Let's just drag this. Perfect. Alright, there. I've set up again. Now, let's go ahead and erase this. We'll get into some problems with these. So the first one is going to be the limit as x approaches 0 of the sine of 3x divided by x. So it looks a lot like the sine of x over x, but instead of that, it's the sine of 3x divided by x. I know some of you out there probably know this material already and are like, why don't you just use L'Hospital's rule? Well, that's coming, but we haven't taught derivatives yet. And sometimes you're not allowed to use that. You have to do it without it, but there's a way to solve these limit problems without using L'Hospital's rule and derivatives. This just requires more algebra. But the idea is, when you solve these limit problems, you want what you're dividing by to be the same as what's inside of the trig function. So we need to make that x a 3x. Well, how are we going to do that? And keep in mind, we can't change the overall value of the function. We have to multiply by 1. Well, how do we do that? So what if I multiplied the denominator by 3 over 3? What if I do that? So if I take the limit as x approaches 0 of the sine of 3x divided by x times 3 over 3, well, 3 over 3 is 1, right? I technically have not changed the value of this function, but you're going to see what's about to happen. We're going to end up getting the limit as x approaches 0 of the sine of 3x divided by 3x divided by 3. Now, at the very least, we have gotten the 3x now in the denominator as opposed to just x. We have something we can work with. But we have a complex fraction, so we need to invert and multiply. So let's go ahead and do that here. This would be the limit as x approaches 0 of the sine of 3x, all divided by 1, all over 3x divided by 3. I think it's nice to put that guiding 1 because that helps you understand the inverting and multiplying. So now let's actually invert and multiply. So the limit as x approaches 0 of the sine of 3x all over 1 times 3 over 3x. Well, what do we got now? This would turn into the limit as x approaches 0 of 3 times the sine of 3x divided by 3x. Now notice we have it set up a lot nicer where what's inside the sine function is exactly the same in the denominator. That's what we're looking for. But you have this extra factor of 3 on the sine as a coefficient. Remember, a property of limits is you can move the constant multiple outside of the limit and multiply the limit by that constant multiple. So this could turn into 3 times the limit as x approaches 0 of the sine of 3x divided by 3x. And now that we have the sine of 3x divided by 3x, we have the same quantity inside the sine function and in the denominator. that limit's just going to go to 1. That's the idea. The limit's just going to go to 1, but you have that extra factor of 3, which would give you 3 times 1. So the limit in this case is 3. So you would actually end up getting a limit of 3 in this case. And I got plenty more like this, but these are largely how you're going to do these types of trig limits. Now, feel free to pause, rewind this video. This might be a bit of a long lesson, but these are some very good problems to understand exactly how we work these limit problems out. I got plenty more. Alright, so we're taking the limit as x approaches 0 of the sine of 4x divided by the sine of 6x. Well, again, if we do direct substitution, you would get the sine of 0 over the sine of 0, which would give you 0 over 0, which is an indeterminate form. Well, that's a problem. So how are we going to remedy that? We don't have anything we can work with just yet. But what you need to do, we need to convert each the numerator and denominator into a form of the sine of x divided by x. How do we do that? So my suggestion is, in this case, is we're going to take the limit as x approaches 0 of, alright, so that numerator of sine of 4x, let's take the sine of 4x, and now we're going to multiply that by 1 over x, and then we're going to do the same thing to the denominator. Divide that by this, take the sine of 6x times 1 over x. Okay, that's great, but why did we do the 1 divided by x? Well, we want it in the form of sine of x divided by x, and if you did the same to both numerator and denominator, you technically haven't changed the value of the function, because the 1 divided by x's would cancel out. But we're making this in a form we can work with. So now you have the limit as x approaches 0 of the sine of 4x divided by x all over the sine of 6x divided by x. Well, we're still not done yet. The reason being is we need to make the numerator, that x in the denominator of the numerator, that needs to turn into a 4x. So how are we to do that? Well, we need to multiply the numerator by 4 over 4, which is multiplying by 1. We technically haven't changed the value of the function. We're just trying to convert this into a 4x. And then you have here, in the denominator, sine of 6x over x, we need to convert the denominator of the denominator into a 6x. So we multiply that denominator by 6 over 6, and we still haven't changed the value of the function. Now let's see exactly what you're up against. So this would turn into the limit as x approaches 0 of 4 sine of 4x all over 4x all over 6 sine of 6x divided by 6x. Well, now we got this in a form we can work with. A couple of great beautiful things we can do here. Remember, the limit of two quotients is equal to the quotient of the two limits. And plus we can apply the constant multiple rule. So let's do that. if we just take the limit of the numerator, we can definitely move that 4 out front. This would equal 4 times the limit as x approaches 0 of the sine of 4x divided by 4x all over that 6 times the limit as x approaches 0 of the sine of 6x all over 6x. Now we notice in the numerator and denominator we got forms we can work with. 4x for the sine and then 4x in the denominator there means this limit goes to 1. So we would end up getting 4 times 1 is 4 in the numerator divided by 6 times this limit, sine of 6x divided by 6x. The limit as x goes to 0 of that is going to be 1. So 6 times 1 is 6. This goes to 4 over 6, which reduces to 2 over 3. So the limit in this case would end up being 2/3. Alright, now let's change it a little bit here. The limit as x approaches 0, actually let's do t goes to 0. They just changed the variable on you. Doesn't matter what the variable is, same process. The limit as t approaches 0 of the tangent of 6t divided by the sine of 2t. So now we have a tangent in the numerator, and then we have a sine in the denominator. If you try to just plug in 0, you'll get 0 over 0, which is an indeterminate form. So we can't do direct substitution. In fact, none of these we can, because you would get indeterminate forms. So what are we going to do? Well, the good news is, if we recall from the beginning of this lesson, the tangent of t over t, or tangent of x over x, that limit as it goes to 0 is also 1. That means we need to convert the tangent form into ultimately tangent of 6t divided by 6t and the sine of 2t divided by 2t. But how are we going to do that? So we need to be creative and do this in a way where we don't change the value of the function. So let's take the limit as t approaches 0 of that tangent of 6t, all that times 1 over t, divided by the sine of 2t times 1 over t. Now, multiplying both numerator and denominator by 1 over t hasn't changed the value of the function. This is just putting it in a form we can work with. So what you'll get is the limit as t approaches 0 of the tangent of 6t all over t all over the sine of 2t all over t. Well, we're almost there. The thing is, in the numerator, the t in the denominator of the numerator needs to be a 6t, and then the t in the denominator of the denominator needs to be a 2t. So how do we do that? So we have to again multiply numerator and denominator by 1. Well, in order to get 6t, when I need to multiply by 6, so if I multiply the numerator by 6 over 6, I've technically multiplied by 1 and haven't changed the value of the function. Then if I multiply the denominator by 2 to get the 2t, well, this would have to be over 2 times 2. I still haven't changed the value of the function. So that's going to make this into a form we can work with. Let's see what we're working with now. The limit as t approaches 0 of 6 tangent of 6t divided by 6t all over 2 sine of 2t all over 2t. Now we have the numerator and denominator in a form we can work with. Well, let's apply the quotient rule for limits. This would end up, and also the constant multiple rule. So in the numerator, you would get 6 times the limit as t approaches 0 of the tangent of 6t all over 6t divided by 2 times the limit as t approaches 0 of that sine of 2t over 2t. And now, in the numerator, tangent of 6t over 6t, the limit as t goes to 0 of that would just go to 1. So this would turn into 6 in the numerator, and then the denominator, 2 times that limit as t goes to 0 of the sine of 2t over t, the limit goes to 1. So you would just get 6 divided by 2, giving you a limit of 3. So the limit of this particular problem is 3. All right, let's change it a bit now. We're going to take the limit as theta goes to 0 of the cosine of theta minus 1 all over the sine of theta. So this is a bit different. We have the limit as theta approaches 0 of the cosine of theta minus 1 divided by the sine of theta. Well, direct substitution gives you 0 over 0 in determinate form. For one, we can definitely apply the conjugation technique, which is what I'm going to suggest. So let's apply the conjugate rule to solve this. This would end up being times the cosine of theta plus 1 all over the cosine of theta plus 1. And now what you're going to get is the limit as theta approaches 0 of the numerator would end up being the cosine squared of theta minus 1 all over the sine of theta times the cosine of theta plus 1. Well, the numerator still, we're going to end up getting an indeterminate form, but the numerator is going to be a big game changer. If we remember the Pythagorean identity, cosine squared of theta plus sine squared of theta equals 1. That's a huge Pythagorean identity. So if I take the cosine squared of theta minus 1, that's just going to equal negative sine squared of theta. So this turns the numerator into negative sine squared of theta. So the limit as theta approaches 0 of negative sine squared of theta all over the sine of theta times that cosine of theta plus 1. Well, right now you still have 0 over 0, but it's about to get a little bit better because we notice we can cancel out a factor of sine of theta. This would turn into the limit of theta approaching 0 of negative sine of theta divided by cosine of theta plus 1. Well, if you put 0 into the denominator, you'll get a denominator of 2. Because you can now do direct substitution. Negative sine of 0 all over cosine of 0 plus 1, that would equal negative 0 all over 1 plus 1, which would just give you 0. So this particular limit actually goes to 0 when you apply the conjugate rule. Now here's a good one. The limit as theta approaches 0 of the sine of the cosine of theta all over secant of theta. You're going to look at this. This looks hideous at first. You're probably looking at it like, you've got to be kidding me. What the heck is this? Well, believe it or not, we can do direct substitution, because in the denominator, the secant of 0 is 1, isn't it? Cosine of 0 is also 1, so we didn't have to pull any fancy techniques with this. Let's go for direct substitution. This would give you the sine of the cosine of 0 divided by the secant of 0. Well, cosine of 0 is 1. That gives you the sine of 1 divided by 1, which would just give you the sine of 1, which, if you're wondering what that is, let's round to about 2 decimal places, whatever the heck the sine of 1 is. I get about 0.84. So this limit would be approximately 0.84. It's exactly the sine of 1, or approximately 0.84. Alright, let's go onward. As you do these limits, they'll mix in other limits, make you think it's harder than it really is. Oh, good one, good one. Limit as t approaches 0 of the sine squared of 3t divided by t squared. This looks pretty hideous, doesn't it? Because you have quadratics now in the numerator and denominator. And this would be indeterminate. If you put in 0 for the t's, you would get 0 over 0. It's really not as bad as it looks. Let me show you. Well, we know a quadratic is the same thing as multiplying the two linear factors. So this would be the limit as t approaches 0 of that sine of 3t all over t times another sine of 3t all over t. Now all of a sudden this isn't so bad. We just have the product of two linear factors. This is something we can work with. So let's do that here. In fact, we also have a product rule for limits, that the limit of two products, well, that's just the product of their limits. So this would turn into the limit as t approaches 0 of the sine of 3t divided by t times another set of that, the limit as t approaches 0 of the sine of 3t divided by t. Okay, well, we need to make that t a 3t, don't we? On each one. We have two of the same thing. So that means for both of these, we need to multiply the denominator itself by 3 over 3. So this would turn into the limit as t approaches 0 of the sine of 3t all over t times 3 over 3. We technically haven't changed the value of the function. We're just trying to get a 3t. And then we're going to do the same thing to the other one. The limit as t approaches 0 of the sine of 3t all over t times 3 over 3. Well, let's simplify. You get the limit as t approaches 0 of sine of 3t all over 3t all over 3. You're going to get that on both counts. Well, we have two sets of complex fractions that we have to invert and multiply. I know this is looking really horrendous, but let's do it. And in fact, you know what? I hate to say this, I'm going to start erasing a bit. So if you need the steps I got, please feel free to rewind to see how I got there, but I'm going to at least start erasing this as I go. Let's come up here. So we're on to the complex fractions part. This would be the limit as t approaches 0 of the sine of 3t all over 1 times 3 over 3t. And yes, we're going to do the exact same thing to the other set of this limit. The limit as t approaches 0 of the sine of 3t all over 1 times 3 over 3t. Let me erase a little bit more. In fact, I think we see where we're at now. So let's simplify one more time. This would be the limit as t approaches 0 of 3 times the sine of 3t all over 3t. And then it's going to be the exact same thing for the limit it's multiplied by. The limit as t approaches 0 of 3 times the sine of 3t all over 3t. Well, we can use the constant multiple in each of these. This would turn into 3 times the limit as t approaches 0 of the sine of 3t all over 3t times the quantity of 3 times the limit as t approaches 0 of the sine of 3t all over 3t. And now notice we have two forms we can work with. The limit as t approaches 0 of sine of 3t over 3t is going to go to 1 for each of these. So you're just left with 3 times 3, which is going to give you a limit of 9. So this limit actually goes to 9. We did all that work just to get to 9 for our limit. Alright, let's do another here. we have the limit as x approaches 0 of the cotangent of 2x all over the cosecant of x. Alright, so the limit as x approaches 0 of the cotangent of 2x all over the cosecant of x. Well, we've dealt with sine, cosine, and tangent, right? So it might be helpful to rewrite this limit in terms of either sine, cosine, or tangent. But first, why don't we break this up into what we really have? Isn't this the same thing as the limit as x approaches 0 of the cotangent of 2x all over 1 times 1 over the cosecant of x? If you know how to split up your numerator and denominator into two separate products, this is actually going to go a long way. And you're about to see what I'm doing here in a second. So, cotangent, isn't that the same thing as the reciprocal of the tangent? So this would just turn into the limit as x approaches 0 of 1 over the tangent of 2x times, now what's the reciprocal of cosecant? 1 divided by the cosecant, well, that's simply the sine. That would end up being the sine of x. So let's show you what you're really working with here. This would turn into the limit as x approaches 0 of the sine of x divided by the tangent of 2x. Well, now all of a sudden we got this in a form we can kind of understand. But you're still presented with a dilemma. At first, if we plugged in 0 into each of these in the numerator and denominator, we didn't even get 0 over 0. The limit just doesn't exist for cotangent at 0 or cosecant at 0. Now we're at least into an indeterminate form where you get 0 over 0. We have a hope of being able to do something with it, but in order to put this into a form we can work with, don't we need to have a divided by x in both the numerator and denominator? So here's what we're about to do. We are about to do this. So the limit as x approaches 0 of the sine of x times 1 over x all over the tangent of 2x times 1 over x. And you notice I multiply both numerator and denominator by 1 over x, meaning I technically haven't changed the value of the function since they would cancel out. Okay, so what did this just turn into? This turns into the limit as x approaches 0 of the sine of x divided by x all over the tangent of 2x all over x. We're almost there. The only problem is, in the denominator, you have tangent of 2x divided by x. That x should become a 2x. So really and truly, we should multiply that denominator by 2 over 2. And we still haven't changed the value of the function because 2 over 2 is 1. We're just trying to convert that into a 2x. So let's see what we really get now. You'll get the limit as x approaches 0 of the sine of x divided by x all over 2 times the tangent of 2x divided by 2x. And now notice you have both numerator and denominator in a form you can actually work with. we can now apply the quotient rule for these limits, and why don't we go ahead and do that? So this would turn into the limit as x approaches 0 of the sine of x all over x divided by, we can take the limit as x approaches 0 of the denominator. Let's move that 2 out front, so that'd be divided by 2 times the limit as x approaches 0 of the tangent of 2x all over 2x. Now we have the limits. Well, the limit as x approaches 0 of the sine of x divided by x goes to 1. And then the limit as x approaches 0 of the tangent of 2x divided by 2x also goes to 1, but you're multiplying by a 2 times that. So you would end up with 1 divided by 2, and that's your limit. The limit of this function actually goes to 1/2. I know that one seemed like a bear to try to pull off, and it kind of was with all the steps, but the limit ends up being 1/2. I have 3 more, then we'll be done. Okay. The limit as x approaches pi over 4 of the sine of x minus the cosine of x all over the cosine of 2x. Alright, well, if you put that pi over 4 as direct substitution into the numerator, you end up getting 0. And then if you put it in for x in the denominator, that turns into the cosine of pi over 2, which is also 0. So you actually get 0 over 0. This is undefined. Well, in the denominator, there's a very important trig identity. If you remember what the cosine of 2x is back from pre-calc, that is going to be equal to the cosine squared of x minus the sine squared of x. The cosine of 2x equals the cosine squared of x minus sine squared of x. So remember back in pre-calc when I was saying, remember some of these fundamental trig identities, you're going to use them in calculus. Well, case in point right here. This is a very important trig identity that you're going to use from here till the end of time throughout your math career, really. Not just in Calc 1, but all over. So what we should do first is go ahead and convert this. So this would become the limit as x approaches pi over 4 of the sine of x minus the cosine of x divided by, that cosine of 2x is the cosine squared of x minus the sine squared of x. Well, where am I going with this? The good news is this is the difference of 2 squares, so we can actually factor this. This is going to turn into the limit as x approaches pi over 4 of the sine of x minus the cosine of x divided by, let's factor this difference of 2 squares. This would become the cosine of x plus sine of x times the cosine of x minus sine of x. Well, in the numerator, it almost looks like we have that, except for you have it in reverse order with sine of x minus cosine of x. Well, we could just factor out a -1, and what you'll end up getting is the limit as x approaches pi over 4 of negative of the cosine of x minus the sine of x divided by the cosine of x plus the sine of x times the cosine of x minus the sine of x. And now notice you have a factor of the cosine of x minus the sine of x between the numerator and denominator that'll cancel out. This turns into the limit as x approaches pi over 4 of -1 all over that cosine of x plus the sine of x. And now we can actually do direct substitution, because both cosine and sine of pi over 4 is the square root of 2 over 2. So why don't we do that? This would end up turning into -1 divided by the cosine of pi over 4 plus the sine of pi over 4, which is -1 divided by the square root of 2 over 2 plus the square root of 2 over 2, which would end up giving you -1 all over 2 times the square root of 2 divided by 2, which would actually then end up turning into -1 divided by the square root of 2. But we want to rationalize the denominator, so let's multiply both by the square root of 2 over 2, or by the square root of 2 over the square root of 2. You end up getting negative square root of 2 over 2 for your final answer. So the limit as x approaches 4 of this function would end up being negative square root of 2 over 2. I got two more. All right. The limit as theta approaches 0 of the sine of theta divided by theta plus tangent of theta. So we have the limit as theta approaches 0 of the sine of theta divided by theta plus tangent of theta. And your first thought's probably going to be to conjugate. Or your next thought's going to be to convert that tangent into sine and cosine, get a common denominator, invert and multiply, then conjugate. Either way, you're going to be running around in circles and still come up with an indeterminate form that you can't do anything with. So what are you going to do? It's a diabolical trick, actually. If you just simply have like an x or a theta, conjugating's not your best way to go. Here's what I'm going to suggest you do. First thing you want to do, go ahead, convert that tangent into a sine of theta over cosine of theta. So this would become the limit as theta approaches 0 of the sine of theta divided by theta plus the sine of theta over the cosine of theta. So what I just did is I converted tangent of theta into its sine and cosine identity. Okay, now, again, this trick is best if you just have the variable itself plus the trig function of that variable in the numerator, in the denominator rather. What you're going to want to do is divide both numerator and denominator by the sine of theta. This problem actually stumped me when I was learning calculus because I spent hours trying to conjugate and I wasn't getting anywhere. And this was before I learned L'Hopital's rule, which really shortened the load, which you're going to learn in this course, and you're going to wonder why we didn't do that before. But you have to know derivatives in order to do it. That's the thing. But anyway, divide both numerator and the overall denominator by the sine of theta. And here's what you're going to end up getting. You'll end up getting the limit as theta approaches 0 of your numerator. You divide it by itself, you would just get 1 divided by, now divide everything in your denominator by sine of theta. This would turn into theta over the sine of theta, plus if I divide sine of theta over cosine of theta by sine of theta, I just end up getting 1 over cosine of theta. And this isn't so bad now. Now we can apply both the sum and quotient rules to this limit problem. So here's what we're going to do. We're going to turn this into the limit as theta approaches 0 of 1 divided by the limit as theta approaches 0 of theta over sine of theta plus the limit as theta approaches 0 of 1 over the cosine of theta. Now we have this all in a form we can work with, because the limit as theta goes to 0 of 1, the limit of a constant itself is just that constant. That's just going to be 1 divided by, now the limit as theta approaches 0 of theta over sine of theta, this is in the form of x over sine of x, that limit just goes to 1, plus, now the limit as theta goes to 0 of 1 over cosine of theta, well, cosine of 0 is 1, so you'd have 1 over 1, which is just 1. So in the end, you end up with a limit of 1/2. So this trick is best if you just have the variable plus the trig function of that variable in the denominator. Had you had another trig function of theta instead of tangent, then you'd probably be wanting to use conjugate method. That's the difference. So keep this trick in mind. Now I have just one more problem, and it's going to look bad, but it's actually not. I promise you, it's not that bad at all. Alright, so we have the limit as x approaches 1 of the sine of the quantity of x minus 1 all over x squared plus x minus 2. At first glance, this doesn't look very friendly, but you're going to see it's not that bad at all. So you notice, of course, if you put in 1 for any of these, you'll end up with 0 over 0, which would be indeterminate. But we can definitely factor that denominator. It's a simple quadratic equation that factors very nicely. This would turn into the limit as x approaches 1 of the sine of x minus 1 all over, we can definitely pull out a factor of x minus 1 in the denominator, then times x plus 2. If we FOIL these out, we'll get x squared plus 2x minus x, so plus x minus 2. So yes, we did factor correctly. Well, we have our factored denominator. What are we going to do with that? Isn't this the same thing as the limit as x approaches 1 of the sine of x minus 1 all over x minus 1 times 1 all over x plus 2? Now we got this into a form we can actually work with. Well, the product of two limits, the limit of two products is the product of their limits. So we can take the limit as x approaches 1 of the sine of x minus 1. I meant to put that inside here. All over x minus 1, we'll take the limit as x approaches 1 of that, times the limit as x approaches 1 of 1 over x plus 2. Well, let's look at this first quantity. The limit as x approaches 1 of sine of x minus 1 over x minus 1, since you have the same thing in the trig function as you do in the denominator, that limit's just going to go to 1. So this would end up being 1 times... Now, if we put in 1 into the denominator of the second product, you just get 3. So this would be 1 times 1 over 1 plus 2. Well, 1 times anything is itself, so you just get a simple limit of 1/3. So the limit in this case would be 1/3 as x approaches 1. So these are some very important trig limit identities. And then these are how you work out some very common problems. So let's see. We're about to, in the next few lessons, we're going to transition into derivatives. The next lesson, we're going to talk about the slope of a tangent line again, as well as the slope at one point on a curve using a limit formula, and then we'll talk about instantaneous rates of change and instantaneous velocity. And then after that, we're going to start getting into derivatives. So I hope everybody has a great day. Take care.